right, we are now recording. We'll go from current slide. And there's one announcement that I know I haven't made before. I kind of doubt that any of you are going to be interested in it, though you may be. I mean, it's a perfectly great deal. But you may know of someone who would be interested in this. What this is, Austin State has been partnered with Alabama Power and various utility and contracting companies to run a special course for them through our workforce development program, and this is line worker training program. Okay, these are the folks that go out there and climb the poles and do the maintenance and fixing of. A lot of times they use bucket trucks, by the way, too. They don't do that much climbing a pole. So they got to be able to, and because some poles are not in areas where you can get a truck to them, so they would have to climb those. So this is a program to prepare people for this work. The program information, now, what I'm getting at is if you know of anyone, you yourself or someone else, who might be interested, one of your brothers might be, no, okay, in climbing poles. The applications, now here's the bad news. Applications are only being accepted today and tomorrow. This has been open for a while, but I didn't get the email until recently. Okay, so it's today and tomorrow, the last 2 days that they can apply for to participate in this program. The training will actually be happening from June 8th through August 14th. Okay, that's 9 weeks, and it will be meeting Monday through Friday from 8 to 4. Okay, 5 days a week, 8 hours a day. I imagine there's probably an hour for lunch or so. The tuition for this is $4,150 plus fees. Now the fees include books, PPE, and I don't know what that stands for, if it's some type of professional certification or training or something like this. I don't know what that stands for. CDL physical, I know what that stands for, commercial driver's license physical. They have to pay for that on their own. There are also permits, licensing, and exam fees, because this course will require a statewide exam or a district or some type of exam to be qualified to do this. Those fees also are included. Not in the $4,150. You'll have to be paying those plus fees. However, don't let the cost get in your way, because scholarships are available. Evidently, they're hurting for people to do the line work that needs to be done. And if you think about it, with all the wild and crazy weather we've been having, they really are needing a lot of people to work on lines. The more severe the weather is, the more you need this. And I bet you, now that the baby boomers are sort of getting toward retirement age, there are fewer and fewer people. A lot of people are probably retiring from this work. So it's a great opportunity. I think it pays quite well. So this $4,150 plus fees is not a bad cost. Here are the program outcomes. When they complete the course, they will be OSHA 10 certified. Okay? OSHA stands for Occupational Safety and Health Administration. I think that's what it stands for. OSHA 10 sounds pretty good. Okay? That's OSHA 10 certification. They'll also have their commercial driver's license, because these folks have to be able to drive those big crane trucks, okay? And that requires a commercial driver's license. So you'll also get your commercial driver's license in this course. You'll also get cardiopulmonary resuscitation training, CPR training. Another big bonus that can be used in a variety of fields, as can commercial driver's license. And you'll get, of course, basic line worker skills. How to do the job that's required to repair, replace the power lines. it's also we work for the phone companies and people like that as well. If you want more information about it, now remember, you only have the day and tomorrow to get this information. It's here at Lawson State Community College, Office of Workforce Development, and Dr. James Gray is our Workforce Development Manager. I'm pretty sure he's over in the Ethel Hall building, right across the parking lot here. If he's not, he may be back here in the Millsap building, but I believe he is on this campus. He's our Workforce Development Manager. I have a phone number for him. This is why I think it's on this campus, because most of the phone numbers on this campus start with 929-3519, 3449. So this sounds like one of our numbers over here. And Mr. Tommy Hobbs is the Assistant Dean for Workforce Development. I'm almost certain his office is there in the Ethel Hall building. Now, to apply for this, folks who just come in, this is line worker training program. Unfortunately, I didn't get this until yesterday, so I haven't been announcing it. The last 2 days to apply for this program are today and tomorrow, okay? And this is training that will be offered here in the summer, June through August, and it's through our workforce development. To apply for the program, you have to go to a website. It's eventbrite.com, and a bunch of slashes and stuff, pre-apprentice power line worker application tickets, okay? So they need this information. So if you know of anyone who might be interested in becoming a line worker, it pays pretty well, and for people who like to climb and do this kind of things, I would say it's a very nice, lucrative profession to be in. My younger brother worked for a small power company. It used to be called an REA, but now it's just called the Energy Corporation. And those line workers, I think, make pretty good bucks. Okay. So we have had a few more people come in. Amari was not one of them. Austin not one. Ja'Cory was one. Is one. Okay. Aaron is not here yet. Eddie is. Okay. Nikhil, not yet. Brandon is. And David was already here. Ian has not come in yet. So it's 1, 2, 3, 4, 5, 6. It's a little low, but hopefully the others will be coming in. All right. Any questions on anything we've covered so far? Or any questions at all? Okay. All right. We're in Chapter 4, Trigonometry. That's the science or the study or measurement of triangles. We're in 4.6, which is graphs of other trigonometric functions. 4.5, we did sines and cosines. 4.6, we've already done tangent and cotangent. We're getting ready to do the other two functions, which they call the reciprocal functions. So we're on page 311, top of the page, graphs of the reciprocal functions. Now, there's other reciprocal functions. Cotangent is the reciprocal of tangent. Sine is the reciprocal of cosecant. Cosine is the reciprocal of secant. Yeah, there's others. They're talking about cosecant and secant. Okay? You can obtain, okay. These have the weirdest graphs in my mind, okay? Sines and cosines, yeah, they're pretty simple. They look a lot alike, okay? These go on. Tangent, cotangents, they have this vertical asymptotes, but they're pretty regular. These look a little odd, but they're some of the easiest ones to do because guess what? You use the sine and cosine functions to determine. And you sort of use sine and cosine functions to determine the graphs of tangent and cotangent because anywhere that the cosine was 0, you knew the tangent had to have vertical asymptote because tangent is sine divided by cosine. So anywhere the cosine was 0, tangent's not defined. Okay? And cosine is, cotangent is cosine divided by sine, so anywhere the sine is 0, vertical asymptote for a cotangent function. Same thing goes here, except now it's just reciprocal, so that's even, in many senses, easier to draw. You can obtain the graphs of the two remaining trigonometric functions, cosecant and secant, from the graphs of sine and cosine because they are reciprocal of them. Okay? So, if you're trying to graph this one, graph sine. If you're trying to graph secant, graph cosine first, and then you'll do the graph of the other. For instance, at any given value of x, the y-coordinate of the secant is reciprocal of what the cosine is. Okay? The y-coordinate of the cosine. So it's a 1/, relationship. Of course, when cosine is equal to 0, reciprocal does not exist, so they're vertical asymptote. Near such values, the behavior of the secant function is similar to that of the tangent or cotangent. Just takes off and goes. More like tangent because tangent is sine over cosine, so they are very, very similar where cosine is equal to 0. In other words, the graphs of tangent x, which is sine over cosine, and secant x, which is 1 over cosine, very, very similar. Difference is tangent x goes from negative infinity to positive infinity. Secant x does not. It goes both places, but it has a big gap in the middle. Both of these do have vertical asymptotes wherever the cosine is 0. And where is the cosine equal to 0? What values of x? Not quite as hungry, you all eat up. Half pies, okay? Okay? The half pies. Pi over 2 plus n pi, where n is any energy. Similar, the cotangent of x is cosine over sine, and cosecant of x is 1 over sine. So those are going to have, anywhere where sine is 0, those are going to have vertical asymptotes. And where is sine 0? If you're really hungry, you whole pies, okay? N pi, okay? So 1 pi, 2 pi, 3 pi, or 0 pi, whether that's who it is, okay? That's where your cotangent and cosecant have vertical asymptotes. So that's actually, first thing, in my mind, graph the sine or cosine depending on which secant or cosecant you're dealing with, and then put in your vertical asymptotes. So to sketch the graph of the secant or cosecant function, you should first make a sketch of its reciprocal function. What's the reciprocal of secant? The other one. Cosine. Reciprocal of cosecant? Sine. Exactly. So first make the graph, sketch the graph of its reciprocal. For instance, to sketch the graph of y is equal to the cosecant function, which would you sketch? Sine function, exactly. Then take the reciprocals of the y-coordinates to obtain the points on the cosecant. And really, I don't mess with taking reciprocals, I just draw them, okay? You'll see, it really turns out being pretty easy. All right. I wish they did this in pieces rather than just showing the whole thing. But if you're graphing y is equal to cosecant, first graph y is equal to sine. We know how to do that. Sine starts at 0, max at pi halves, and by the way, if it's just sine x, the max is at 1. Okay? Notice your a is 1, your b is 1, your c is 0. So just graph the regular old sine function. It goes 1 at pi halves, 0 at pi, negative 1 at 3 halves pi, and back to 0 at 2 pi. And going the other way, same thing. Negative 1 at minus pi halves, 0 at minus pi, and so on and so on. So first graph that sine function. Okay? Next thing we do is mark Nikhil here. Okay. So after you graph the sine function, that's not what they asked for. They asked for cosecant. Graph the sine. Everywhere the sine crosses the x-axis, per vertical asymptote. And they do dotted red lines, except for the y-axis. I would put a dotted red line on top of the y-axis and then do that. Those are your vertical asymptotes right there. Next, find your max and min. Here's a minimum value. 1 over minus 1 is minus 1, right? But rather than going up like the sine do, these go down. And here's a vertical asymptote here, a vertical asymptote here, so these go down. When find your max, max is at pi halves. Plus 1 is the value of sine. 1 over some 1 is 1. So they kiss at the max and the min, and then they go in the opposite direction. Kiss and leave. Okay. So they go. Kiss here, go down. So you see the cosecant function is never defined for its value. Output is never between minus 1 and 1. It can be minus 1 where it touches, and plus 1 where it touches, but it always is outside of those. So you go where sine stays in between those, cosecant goes outside of those. Make sense? So the vertical asymptotes at the where sine is 0, and then where they kiss, go in the opposite direction. And that's all you do. There's no calculations or anything else. Figuring out where the sine goes, and then put the vertical asymptote, and then go. For the secant function, same thing, only use the cosine function. Cosine starts at 1, if it's a regular, y is equal to cosine x. A is equal to 1, b is equal to 1, c is equal to 0. So it starts here, goes down to 0 at pi halves, down to minus 1 at pi, up to 0 at 3/4 pi, 3/2 pi, and back to 1 at 2 pi. Going in the opposite direction, goes down to 0 at minus pi halves, down to minus 1 at minus pi, and keeps going. As soon as you get the cosine functions wrong, it's the vertical asymptotes where the cosine is 0, and then where the max and min are, that's where they touch and go in opposite direction. And that's all you do. That's all you do. Get the vertical asymptotes in place where the cosine is 0, and then touching at the max and min, go in opposite direction. And again, cosecant is never between minus 1 and 1. It will be minus 1 where cosine is minus 1. It will be plus 1 when cosine is plus 1. Outside of that, it's always the bigger number, absolute values, cosine stays between minus 1 and 1. So here are the characteristics of it. Because it's reciprocal, the cosecant is reciprocal of sine, then the sine period is 2 pi, so is the cosecant. Okay? Domain would be all those places except where sine is 0. That would be at the whole pi. So all x's not equal to n pi. Okay? What's the range? The range goes from minus infinity to minus 1, then, and it includes minus 1. Okay? Then it picks up at 1, which it includes 1, and goes to positive infinity. Okay? Vertical asymptotes are the places where the domain was not defined. Those are your n pi's. It's symmetric, just like the sine is about the origin. So whatever it's doing here, it does the opposite over here. Now, the secant function, reciprocal of cosine, so its period is also like cosine, 2 pi. Domain for all x's not half pi's, because cosine is 0 at the half pi's, so any of your half pi's are not defined. In fact, that's where your vertical asymptotes are. The range, just like the cosecant range, it goes from negative infinity up to and including negative 1, and picks up at positive 1 and goes to positive infinity. Okay? Just like it shows here, vertical asymptotes we already said. This is symmetric about the y function because the cosine's an even function, so is the secant. Sine is an odd function, so is the cosecant. Make sense? All right. That's all there is to graphing. The weirdest looking ones, they're pretty easy to graph. Just graph sine and cosine first, then you got the others done. Okay. In comparing the graphs of the cosecant and secant functions with those of sine and cosine functions, respectively. Note that the hills and the valleys, I say maxes and mins, are interchanged. What is a hill for the sine is a valley for the cosecant. What is a valley for the sine is a hill for the cosecant. Okay? I would prefer it's the maximum for the sine is a minimum for the cosecant. What's the minimum for sine is maximum for cosecant. Same thing. For instance, a hill or maximum point on the sine curve corresponds to a valley or a relative minimum point on the cosecant curve, and a valley or minimum point on the sine curve corresponds to a hill or a relative maximum on the cosecant curve, just like we showed. Keep that one in the ground, didn't we? Okay. But that makes them easy to draw. Start there and go up or go down, depending on which way you are. Opposite way from what the sine is doing. Additionally, the x-intercepts of the sine and cosine functions are the vertical asymptotes of the cosecant and secant functions. Now, what are the x-intercepts of the secant and cosecant? Trick question. There are none. They never reach zero. They're always greater than positive 1 or less than minus 1. They never cross the x-axis. Secant and cosecant never cross the x-axis. Ever. Okay. Ever. Okay. Unless you have a vertical shift or something like that. Okay? So here's example 4. Sketch the graph of y is equal to 2 cosecant of x plus pi fourths. Where would you begin? Where would you begin? Second? Okay. I'm with you there except for one thing. I do one thing first. Where does A, B, and C make more sense? Sine and cosine functions. So first get the sine or cosine function. Which one would relate to cosecant? Think again. Sine. Okay. So we're first going to graph y is equal to, keep the same A, B, and C, to sine of x plus pi fourths. Okay. Now now is your turn. What do we identify? A is equal to 2. B is equal to 1. Now what does B tell us? The period is, for sine, 2 pi over b. B is 1, so it's just 2 pi. Right? All right, next. Next. C is equal to what? Not quite. Nope. Negative pi fourths. Remember, the standard form is a sine x plus, or bx, minus c. Remember, anything you're doing with the x, you always, it's opposite. So it's a minus c. Okay? Okay, we'll get there in a minute. So c is minus pi fourths. All right? Now, we forgot something. Once you get the period, what do you do? Divide by 4. That gives you your intervals. And what is that? Pi halves. Okay. Now we're ready to, well, not quite. You need to take the least common denominator between your interval and your phase shift, because C tells you your phase shift. Well, that's quarter. So I'm going to have to make my intervals quarter pies, not the intervals, but where I'm going to mark them is quarter pies. So I'm going to bring down my y-axis, my x-axis, and do 1, 2, 3, 4, 5, 6, 7, 8, negative 1, 2, 3, 4, 5, 6, 7, 8, positive 1, 2, 3, 4, 5, negative 1, 2, 3, 4, 5. Okay. Now, where do we start? Say again? Normally you would, except for the phase shift. So you go, oh, let me put in my thing. Remember I said their interval is pi halves, but I'm going to have to grade it in pi quarters because that's where the phase shift. So this is pi quarters, this is pi halves, and this would be pi, and this would be 1, 2, 3, 4, 2 pi. Okay? This will be minus pi quarters, minus pi halves, minus pi, and 1, 2, 3, 4, minus 2 pi. This will be 1, 2, 3, 4, 5, and negative 1, 2, 3, 4, and 5. Okay. So, again, where do we start? Okay, we normally would, except for the phase shift. So start with the phase shift. What would have been at the origin, which was 0 for sine, we start at pi fourths. So there's your starting point, right? At minus pi quarters, your phase shift. Okay, then your interval is pi halves, so it's 2 quarter pies. So the next one's going to be here, and by then you go up to your amplitude. Your amplitude is 2. So you start at 0 here at the phase shift, and then go one interval over, and that gets you up to plus 2. Another interval over, you're back down to 0. Another interval over, you're down to minus 2. Another interval over, you're back up to 0, and then you don't see the next interval. Okay? Going in the opposite direction, one interval over, you're down to minus 2. Another interval over, you're up to 0. Another interval over, you're up to plus 2, and then you don't see what happens next. So here's basically what's going on here. And you don't need to make this too major because this isn't what you're after. That's just to give you started, right? What you're after is what? Cosecant function. But you got to get that sine function drawn using your A, B, and C. Now I'm going to go to red because guess what I'm going to do next? Say again? I can't hear. I'm going to do my vertical asymptotes. They're always where sine is 0. This is your sine curve, so draw in your vertical asymptotes here, and here, and here, and here. Do your vertical asymptotes next. Now, I'll ask for what color you want your cosecant to be. You pick another color. I'd say not red and not black. Blue. Okay. Carolina or dark? Dark. Okay. Got an NC State fan. Okay, never mind. All right. My dad went there. My uncle went there, so I'm sort of favorable to that too. So how do we do our cosecant function given this? Start at the max or min, and it's the max for sine, so it's the min for cosecant. and then head toward the vertical asymptote here and on that side as well. Start at the min here, and that's your max for these. So head in the opposite direction. Here's your max. Start there and go up and up. Start the min here, your max there, go down and down. That's it. That's all you do. There's no other values you put in here or anything else. Just start here and go there. If you can guess where 1/2 is here, which would be a 1 now because half of it is 2, then this would be where your -3 was here. But you don't have to mess with that. Just draw. Okay, get them close. Put the curves in. That's all you do. That's it, folks. The hard part was getting the sign with the amplitude and the phase shift right. Okay? And of course that phase shift sort of messed up your... The period was fine, the intervals were fine, but your phase shift shifts it. You know, so you have to go from there, but you always move one interval at a time. And that's why you do the intervals. Does that make sense? Yay or nay? All right? All right. That's our rendition of it. Let's see how they do it. All right, to erase? So you have to remember how mine looks. So first thing they do, begin by sketching the graph of exactly the same function except put a sign rather than cosecant. Okay? With all the other pieces in place. And that identifies from this function, the amplitude is 2, the period is 2 pi. We figured that too. Okay? Now they do solve these equations. Okay? Where your x plus pi, the thing in parentheses, set it equal to 0 and 2 pi to get the endpoints of that. And you'll see immediately this becomes x equal minus pi 4. That's your starting place where we started before. That's your phase shift. Okay? And then that also shifts 2 places. Half of interval this way. Okay? You can see that one cycle of the sine function corresponds to the interval from minus pi fourths to 7 plus pi. And that's what they're showing here. From minus pi fourths to 7 quarters pi. Okay? That's how they did it. How I did it is do the B pi. B is 1, so your period is 2 pi. Your interval is pi halves. You start from here, and then an interval will be here. There's your max here. Intercept here, a min, here an intercept, and so on. Going this way, here a min, here an intercept, here a max, and so on from there. However you want to do it. I prefer my way, of course, but if you like their way, it's perfectly fine. Okay? All right. And then once you get your sine curve drawn, wherever you have a 0 for the sine curve, it's a vertical asymptote. Every 0 is a vertical asymptote. Cosecant is 1 over sine. You can't divide by 0. And then at the max here, that becomes a min there. Min here becomes a max there. And so on. Always reciprocals. Make sense? Yay or nay? Okay. Because the sine function is 0 at the midpoint and endpoints of this interval, the corresponding cosecant function is not defined there as a vertical asymptote there. So they're at so you see, rather than having to think through this and get those points right, if you just drew the sine curve, anywhere it crosses the x-axis, that's the vertical asymptote, without figuring out this is at 3/4 pi or 7/4 pi or any. Just everywhere it crosses, okay? That you get from your intervals. The graph of the cosecant function is represented by the black curve on the previous slide, which we saw. Okay. They're skipping example 5, so let's go back and do example 5. See how they go. Let's see, maybe that's even better. Okay, we'll do example 5 here. Oh, let me go back to black. Sorry, this past weekend we were doing a lot of yard work and burning some brush and things like this, and I think I breathed too much smoke, and so my throat is just being gurgly and mess. I hope it'll clear soon. It's not as bad as it was yesterday, so I hope it's clearing. And by the way, after every example, there is a checkpoint. Good to do the checkpoints shortly after class, as soon as you can. Example 5, though it's not given in the PowerPoint, it is given at larsonprecalculus.com. There you can see an interactive version of this type of example. So here's the one they want you to sketch now. Sketch the graph of, if I can get my screen to set up, y is equal to secant of 2x. Secant of 2x. Okay? Where would you begin? Yeah, what did you say? The reciprocal function? That was the right thing to say. And what is the reciprocal function for secant? Cosine. Okay? Reciprocal function of secant is cosine. So that would be cosine of 2x. Okay? Where would you go with that? Okay, say again. Okay, so A is equal to 1, so that would imply that the amplitude is 1. Okay, got it? Next. B is equal to? B is equal to 2, right? B is 2, right? The coefficient of your x. And that would imply, what does that affect? The period is what? Say again? A little louder. 2 pi over 2, which is pi. And what you do with that period? And that gives you the interval will be pi fourths. Okay? Next. C is 0, you have no phase shift. D is 0, you have no vertical shift. Okay, good news. We didn't do D before, but you had none. Okay, so we're going to graph that cosine based on what we know. So here's going to be your vertical. There's going to be your horizontal. We'll tick off a few points. 1, 2, 3, 4, 5, 6, 7, 8. And negative 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4. Okay. Now, because your interval is pi fourths, you don't have a phase shift, so we'll do these in terms of that. So there'll be pi fourths, pi halves, pi, 1, 2, 3, 4, 2 pi. And not minus pi fourths, minus pi halves, minus pi, and minus 2 pi. And this will be 1, 2, 3, 4, 5, 6, 7, and negative 1, negative 2, negative 3, negative 4. Okay. For cosine, where do we begin? There is no phase shift, so we begin at, second, 1, 0, 1. So there's where cosine begins. And then where does it go from there? for each interval goes down to 0, down to -1, up to 0, up to +1, down to 0, down to -1, up to 0, and up to +1, and so on and so on and so on. Down to 0, down to -1, up to 0, up to +1, down to 0, down to -1, up to 0, and there. So here is sort of your cosine curve. My ugly drawing. Okay, something like that. What do you draw in now? If you haven't guessed yet, notice I just went through. Say again? Yes, the vertical asymptotes. Where do they go? Everywhere that cosine is 0. There's a 0. There's a 0. There's a 0. I didn't get the curve in the right place. There's a 0. Boy, we've got a lot of them here, don't we? Okay, there's our vertical asymptotes. Then where do we go from there? What color do you want your secant function to be? You choose. Not black, not red. Not white. There, purple, okay? There's purple. So where do we go with the secant function here? Start at the max or the min and go in the opposite direction. Min becomes max, max becomes min, min becomes max, max becomes min, min becomes max, max becomes min, min becomes max. Something like that. That's all you do. I mean, there's no rocket science here. You just start at those max and min points and go in the opposite direction. Just sort of curving up about the same as the cosine curve down, except it's a continuous curve, these are not. So they just head off to infinity, either plus or minus. Does that make sense? Once you get the sine and the cosine curve drawn, these are pretty easy. The vertical asymptote for the other is 0, and then use the maxes and mins to be your mins and your max. And go from there. Just go in the opposite directions. Does that make sense? Okay. Now, we're going to start talking about these damped trigonometric graphs, as if you hadn't already been calling them that. No, you didn't, did you? No. You wouldn't do that, would you? Be sure you put your ED on it. Okay. PED. Okay. Or PE or whatever. Okay. You can graph the product of two functions using properties of the individual function. These are a little tough to do, but not too bad. For instance, consider this function. F of x is x times sine x. Okay? Think of that as a product between the function y is equal to x and y is equal to sine x, the product of two functions. Now, using the properties of absolute values and the fact that the sine x, the absolute value of sine x is always less than or equal to 1. Sine stays between plus and minus 1. That's what this is saying. Absolute value of x, of sine x, is less than or equal to 1. So, I wish they had done this. It would have made it make a little more sense here. Because absolute value, oops, let me go back to black. Okay. Absolute value means it's greater than or equal to 0, right? So if you just put that there, 0 is less than or equal to the absolute value of x. is less than or equal to 1. Right? That's the value of sine x. Now, multiply each of these by x. So you still got 0 there, and then this will be absolute value of x times absolute value of sine x, and then this will just be absolute value of x. You multiplied all three sides of that inequality by absolute value of x. 0 will stay 0. Okay? Now, what does that tell you? This is beginning to look a lot like this. Not exact, but close. What this function is that, right? This would be, you have the identity function on this side, the opposite of the identity function on that side. That's what this is, right? But, okay, we'll leave it like that. And this is the product of that, and of course 0 is 0, okay? So, this function is always less than or equal to that. And for the absolute values in there, it's always greater than or equal to 0. Now, here's something else they're going to do now. When you take off the absolute values here, that then allows it to be the minus of this over here and the plus of that over here. Because taking off the absolute values now allows it to go negative if it needs to. So then you take this and move it over here. And that's what they did here. Minus absolute value of x is less than or equal to x sine x, which is now what your function is, and that's less than or equal to absolute value of x. Now, what does that mean? Absolute value of x was like this, minus absolute value of x is going to be like this. It's going to be the continuation of those, okay? Which means the graph of this one always lies between the line y is equal to minus x and y is equal to positive x, okay? If this is minus x, there's positive x. Now, I'm going to take you back and do something else with it. Furthermore, because f of x is equal to this, and it's plus or minus x at your half pies, because when sine x at the half pies is plus or minus 1, right? So if this is plus or minus 1, this becomes plus or minus x. So they're going to touch each other at the half pies, all your half pies. And they're going to be zeros at your whole pies, because no matter how big x gets, sine x in pi is always going to be 0. So you know your intercepts are going to be the same. What used to be your max and min still are max and min, but now they're going up to x rather than going up to amplitude. That's where I get off and want to show you something else. So n is any integer in both of those, and the graph of f x touches the line minus x or plus x at all the half pies and has an intercept at all the whole pies, because that's what sine does. Now, here's another way to look at it. Remember our function, this one right here? Think of it this way. To me, this makes as much sense, I think a little more sense than this does. I mean, this is all correct. Think of this. What used to go here in front of sine x? Your a. That was your amplitude. That was when the amplitude was a constant. That was a. Plus 2, minus 2, whatever, Now you have a variable amplitude. So it goes up to x and down to minus x. Up to x and goes down to minus x. To me, that's a lot easier to think of in terms of that. When you think of plus x is here, minus x is there, that's the identity function here, identity function there. That's your variable amplitude. So now your sine goes up to At first, it's going to go up a little ways, because it's reaching those two. I don't know. To me, that makes more sense than having to do all this mess. Okay? But if this makes good sense to you, use it. It's all correct. Okay? So the sketch of f is shown below, and the function f of x equals x sine x. The factor x is called the damping factor. And frankly, it seems like it's an explosion factor, not a damping factor. It only damps near 0, okay? It explodes when you get out here. But the other issue here, and this is the thing that will reach out and bite you in the place you don't want to be bitten, and that is this. When x is, okay, sine is an odd function, right? And x is an odd function. But odd times odd happen to give you even. So this becomes an even function here, because when sine x is negative, x is also negative, okay? And sine x is positive, x is also positive. So this, rather than going down here like a sine usually does, it goes up and then down and up. So it's in the opposite direction here, but in the same direction there, okay? So you have to remember this becomes an even function now because you have an odd times an odd. That doesn't work in math, but it works here. Okay. So that's the only thing that's tricky here in my mind. After that, at pi halves you touch, at 3 halves pi you touch, at pi halves you touch. But here you're touching in the opposite way because they're in opposite directions. This is minus times minus gives you plus. Here, here, here. So they just go in the opposite direction. Does that make sense? Oh, and your zeros are still your zeros. 0, pi, 2 pi, 3 pi, negative pi, negative 2 pi, negative 3 pi. The zeros haven't changed. Your positive maxes and mins touch the. And here's the other thing. They call it the damping factor. I call it the envelope. That the sign stays inside the envelope. The envelope's getting big here and big there, so rather than calling it a damping factor, I think of it as the envelope. The sign stays inside the envelope. So that's my thinking. You don't have to think that way. All right. Here's example 6. Whoa, totally different function here. Sketch the graph of f of x is equal to e to the minus x times the sine of 3x. Okay? Now, in this case, going to go on and start my graph here. And we'll do 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7, 8. Positive 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5. Okay. Now, I almost want to do the same thing I did before. What's your A? Okay. It's sort of like e to the minus x. Okay? So let's graph that first. So starting at 0 is pretty easy. What is your e to the minus 0? E to the 0. Anything to the 0th power is? Is what? 7 to the 0th power is? 1. Anything to the 0th power is 1. Okay? Now, remember these. Sorry. Forgot to do my B's. What's your B? 3. What does that imply? The period is 2 pi over 3. So 2/3 pi. Oh. Okay? Now, just because that's a little on the weird, and then your C is 0 and all like this. So because that is a little weird, I almost want to make these intervals, not the interval. The interval, oh, what do we do with this, though? Yeah, we're going to go on and do this. What do we do with that? Divide by 4 to give our interval. And what is that when you divide 2 pi over 3 divided by 4 is multiplying by 1/4, right? Okay, so what does this become? Pi over 6, is that what you said? Say yes. Okay, good. Pi 6. There's our intervals. That makes me happy. So this will be pi 6. This will be pi thirds. This will be 2/3 pi. And this will be pi. Okay? This will be minus pi 6, minus pi thirds, minus 2/3 pi, and minus pi. And it keeps on going. Okay? Now, okay. Now that we've got that in place, if you wanted to, which I think probably you should, perhaps you should do e to the minus pi 6th. Okay? Or if you want to, well, either way you're going to need a calculator. So do e to the minus pi 6 and see what you get. I haven't spaced those too well, but we'll pretend. E to the minus pi 6. Say again? Okay, just a little over, just less than 0.6. So I'll put it right there. Okay, how about minus pi thirds? E to the minus pi thirds. Point what? 35. So that's a little over 1/3. Okay. I'll try to estimate it there. How about e to the minus, this, by the way, is pi halves. E to the minus pi halves. 0.2? 0.20? Okay, that's about 0.2. So it's going to be down here. So you see that is getting less and less and less, right? I bet you the next one's going to be down here somewhere and then down here somewhere. So it's getting really close, okay? Let's go in the other direction. E to the minus of minus will be a positive pi 6. What will that be? One point, say again? 1.68. Okay, so that would be somewhere about 1.7. I'm going to guess that. E to the pi thirds. About 2.7. 2.84. Okay, somewhere up there. This is, remember, minus pi halves, so that will be e to the pi halves. E to the pi halves. Someone help me with that one. I can't do it in my head. Say again? I can't hear. E to the pi halves. 4.81. Say again? Okay. It's almost 5. And I bet you e to the 2/3 pi is going to be off scale, but we'll see. E to the 2/3 pi. Say again. 6.89? Huh? Oh, 10.99. Okay, that is off scale. I can only go up to 6. Okay? What'd you get? Say again? Okay, it's still off scale. I don't care. It's off scale. Okay. Okay, now, because the envelope needs to be top and bottom, because sign can be plus or minus 1, so it could flip this over, we're also going to have an envelope down here, down here, down here, here, down here, just exactly on the opposite side of that. Okay? And up here too. So that was something about like here. And this was just short of -3. And this was short of 5. So it's going to be somewhere down here. So that goes off scale pretty fast. So those are our 2 envelopes. Now that's what I call them. Okay. Now the next easy thing to do is to put in our zeros. Now, because e to the minus x is always positive, sign is going to go back and forth. It's not going to be even now. It's going to be odd. So you got a 0 here, a maximum here, a 0 here, a minimum here, a 0 here, and then sort of a max there. And going backward is going to be a minimum here, a 0 there, and a maximum up here, a 0 there, and then a minimum somewhere down there off scale, another 0, and then another 0 over here. My graph isn't too good. So graphing what we can here, I think I got off somewhere, didn't I? Okay, this is a 0, min, max, min. Oh, this is not a point. I should have used different colors. Okay, so this is going up to here, down to here, down to there, here, there, there, and then it starts just going back and forth. I can't even draw it. This goes down off scale here, comes back up somewhere here, and goes infinitely high here, and then starts coming back down here. So that's your curve, okay? You can't show it all, but that's what's happening, okay? Blowing up going this way, and definitely damping big time this way. So that's, in this case, I would call that a damping function to the positive side. I call it an envelope on either side. So, but you see how you do it. So get your envelope drawn, okay? Once you draw your envelope, then flip it over to do the minus side of the envelope, and then put your zeros in right where they should be, and then put your maxes and min right where they should be. I missed something pretty badly there. And then where you can, connect the dots. Where you can't, just let them go to infinity and come back up. Okay. So, let's erase my ugliness here. And let's see how they do theirs. Consider f is a product of 2 functions, yeah, e to the minus x and that, blah, blah. Okay. For any real number x, you know that e to the x is always positive, not even equals 0, positive, okay? And sign is always between plus and minus 1. Okay, so e to the x is there. So minus e to the x. The e to the minus x, sine 3x is always going to be between minus e to the x and plus e to the x. And that's what why you draw the minus. You do the e to the x and then negate it, flip it over. So, and then they go through this mess, and same thing we did with our b. We got the interval, okay? And you reach the curves at the max and min, and you have your zeros where the zeros are, okay? And then you draw it, okay? And again, here's your e to the minus x. That looks a lot like ours did, didn't it? And here's the minus e to the minus x. That looks a lot like ours. And then the sign starts at 0, goes up to the max here, down to 0 here, min here, 0 there, and then somehow it's going back and forth in between, but it's damping out so quickly you can't tell. Going this way, it goes down to the min, up to your 0. The zeros are regularly spaced, just like they normally would be. Up to a 0, up to a max. Then this one goes off scale down here. This one picks up from off scale and goes up here. That one picks up from off scale. The zeros are still going to be regularly spaced. These lines, just do this from there on. Does that make sense? That is your damped sine curve. And every one of these has a checkpoint. Okay. Are we getting close to out of time? What we got? 11:06? 9 minutes. Okay. All right. I think we've got time for the next slide. Below is a summary of the characteristics of the 6 basic trigonometric functions. Okay, sine, of course, going to have zeros at the whole pi's and maxes and mins at the half pi's. Okay? Always starts at the origin and goes up. Domain, all real numbers, range between plus and minus 1. It's just a regular sine function. Period 2 pi. Cosine, same deal, except it starts at 0, 1. And its zeros are at the half pi's, maxes and mins at the whole pi's, starts at 0, 1, domain all real numbers, range same as sine, between minus 1 and 1, including those, and period is 2 pi. So, nothing new there. Okay? Sine and cosine. Tangent, because tangent is sine over cosine, everywhere the cosine was 0, which was your half pi's here, tangent is going to be vertical asymptote. So vertical asymptote at the half pi's, and zeros at the whole pi, because sine is 0 at intercepts at the whole pi's. Hiccup, sorry about that. And tangent generally is always an increasing function. Okay? The domain is all except the places where cosine is 0, they're half pi's. Range is from minus infinity to positive infinity. The period is only pi's. Tangent and cotangent have periods of pi, the normal period of pi. All the others have a period of 2 pi. Okay? Cotangent function is 1 over tangent. You can think of that or as cosine over sine. I like cosine over sine a little bit better because where cosine is 0, those are the half pi's. That's going to be your zeros for your cotangent. And where sine is equal to 0, at the whole pi's, those are your vertical asymptotes. Okay? So your domain are all x's except those vertical asymptotes at your whole pi's. The range is negative infinity to positive infinity. The period is pi, just like the period of tangent is. But these are always decreasing, unless you have a minus sign in front of them. That will flip them over. So tangent always increasing, cotangent always decreasing, unless you had a minus sign to flip them. All right. Then your cosecant and secant function. Why in the world didn't they draw the sign in here? The sign starts at 0, goes up to plus 1, down to 0, down to minus 1, up to 0, and so on. From here it goes down to minus 1 up to 0. If you had drawn those in here, then everywhere sine is 0, vertical asymptote, that's at the whole pi's, and your maxes and mins for your sine or your mins and your max for your cosecant. Okay? So the domain is all values except your n pi's, because that's where sine is 0. and the range is from negative infinity to negative 1, but including negative 1, union that with positive 1, including positive 1 up to positive infinity. Okay? Same thing for secant, except it's 1 over cosine, so its vertical asymptotes are where cosine is equal to 0, which are your half pi's again, and your maxes and mins for the cosine are your mins and your maxes for your cosecant, so those are the whole pi's. And you just draw them from there. Domain everywhere except the half pi's. Your range from negative infinity up to negative 1, including negative 1, and from negative 1, positive 1, going to positive infinity. Period of 2 pi, because the reciprocal function was 2 pi. All right. How much time now? 4 minutes? Okay, we have time to do our vocabulary. Okay, I'll go back. Whoops, that's not what it doesn't matter. The tangent, cotangent, and cosecant functions are blank, so the graphs of these functions have symmetry with respect to the when you're talking symmetry, you're talking basically evenness or oddness. So what I want to do, and I can't do it now, sorry, what I'll do is do it here. Okay, there's tangent. There's a tangent and cotangent. Okay? Even or odd? They're odd functions, because when it's going this way here, it's going the opposite way there. Coming this way here, it's going that way there. Yeah. Odd functions, and cosecant is also odd. Okay? So the tangent, cotangent, and cosecant are odd. Functions are odd, so the graphs of these functions have symmetry with respect to the what if they're odd functions? The origin. What you always reflect across the origin. They're going in opposite directions from the origin. Okay. Number 2. The graphs of tangent, cotangent, secant, and cosecant functions have blank asymptotes. Vertical, for sure. No horizontal asymptotes here, folks. To sketch the graph of a secant or cosecant function, first make a sketch of its blank function. The reciprocal function, which would be either cosine or sine. Okay? Number 4. For the function f of x is equal to g of x times sine of x, g of x is called the blank factor. You get a little wet, it's damping factor. Okay, good. Okay, damping factor. I like to call it the envelope, but they call it the damping factor. Okay, number 5. The period of y is equal to tangent x is blank. Period of tangent, pi. The domain of y is equal to cotangent x is all real numbers such that blank. Cotangent. Domain of cotangent. Huh? They're not the whole pi's, yeah. All real numbers such that x is not equal to n pi. Okay? Number 7. The range of y is equal to secant x is blank. Range of secant. Negative infinity up to negative 1, and then from 1 to positive infinity. Perfect. The period of y is equal to cosecant x is 2 pi, because it's reciprocal of sign. And this, okay. Homework exercises here, I would do all of 9 through 14. It's just matching. Now, only the odds have answers in the back and at calcchat.com, but you should be able to answer all of those. Okay? Then do any of the odds, 15 to 37, they're all at CalcChat. 19's at CalcView. Do any of the odds 39 to 47, they're all at CalcChat. 49 to 55, they're all at CalcChat, but 51's at CalcView. 57 to 63, they're all at CalcChat. 57's at CalcView. 65 or 67, they're both at CalcChat. 69 or 71, they're both at CalcChat. 73 or 75, they're both at CalcChat. Any of the odds 77 to 81, they're all at CalcChat. And then applied problems 83 or 85, they both should be at CalcChat. True false 87 should be at CalcChat. You can think about doing 89, it should be at CalcChat. There's a graphical reasoning, 91 should be at CalcChat. 93 should be at CalcChat. And we'll be ready for 4.7. How we do it? 1 minute over. Well, there's no extra charge. I'll let you off this time. Okay. All right, so we'll pick up with 4.7 next time. Okay? We only got 4.7 and 4.8 to do before we have the next test. So be trying to wrap up your first test so you'll be ready for the second. Okay, good deal. Any questions? Well, I'm going to